We've worked in vector spaces, then subspaces. Now let's look at the fundamental subspaces. The fundamental subspaces comprise the null space of an n by n matrix A, the column space of the n by n matrix A, the row space of the matrix A, and the left null space of the matrix A. We should start with the null space in this subsection. The null space of a matrix A is made of x element of Rn such that Ax equals the identity element of the plus operation of the vector space Rm, which in fact is the zero vector of Rm, where x is different from the zero vector of Rn. Now, the null space of A is a subspace of Rn. Let's go ahead to show this. For the first condition, we have the zero vector of Rn, which is equals x1 equals 0 to xn equals 0. That is, it's made of 0. For the first condition, we have to show that the zero vector of Rn is an element of the null space of A. Now, the zero vector of Rn is made of n zeros, and A times the zero vector of Rn equals the zero vector of Rm. Since the zero vector of Rn is made of only zeros, with this we see that the zero vector of Rn takes the form of all values which belong to the null space of A, wherein A times the zero vector of Rn is equals the zero vector of Rm. So with this we can say that the zero vector of Rn is an element of the null space of A. The first condition is verified. Let's move on to the second condition. Suppose x and y element of the null space of A. X element of the null space of A implies Ax equals 0, where 0 here is the zero vector of Rm, and Ay equals 0. Adding up these two equations gives us Ax plus Ay equals 0. This implies A into x plus y equals 0. This implies x plus y is an element of the null space of A, and this is because x plus y, when multiplied with A, gives the zero vector of Rm, and so x plus y is part of the null space of A. For the third condition, we have x element of null space of A and C a constant. If x is an element of the null space of A, then Ax equals 0. But C is a constant, so it implies C times A times x equals 0. Obviously, C wouldn't change much. This implies A into Cx equals 0. And finally, based on this, we can conclude that Cx is an element of the null space of A. And this is because Cx, when multiplied with A, gives the zero vector of Rm. With these three conditions verified, we can say that the null space of A is a subspace of Rn. When given a matrix A, which is n by n, let's see how to obtain this null space. We have this 3 by 4 matrix A. To obtain its null space, it suffices to find values of x such that the matrix times x equals O of Rm. Notice that x is an n-dimensional vector, and that's because we have n columns in A. And since the n we get from here is derived from this n, we have 4-dimensional vector x, and O of Rm is 3-dimensional. Since m equals 3, we have 3 rules: 1, 2, 3. This matrix equation boils down to a system of 3 linear equations with 4 unknowns. Let's restructure this equation. We have the matrix put to the left side and then the b's to the right side, where we have x to be unknowns, the matrix, the rows of the matrix to be the constants, and the 0 vector of Rm to be the b's. With this, we'll be able to solve these equations and come up with the solutions, that is, come up with the values for x1 to x4. As usual, we need to put this matrix in its echelon form. Multiplying 1 by 2 gives us 2 minus 2, 0. So we have R2 equals R2 minus 2R1. And to obtain the remaining values, we have 4 minus 2 times 2 giving us 0, 6 minus 2 times 2 giving us 2, 8 minus 2 times 2 giving us 4, and 0 minus 2 times 0 giving us 0. For the next row, we have 3 minus 3 times 1 giving us 0. So we have 3 minus 3 times 1, 0, 6 minus 3 times 2, 0, 8 minus 3 times 2, 2, 10 minus 3 times 2, 4, 0 minus 3 times 0, 0. What we're left to do now is to make sure this 2 turns to 0. We have R2, which we can divide by 2. Then R3 minus R2. So we have 0 divided by 2, 0, 0 divided by 2, 0, 2 divided by 2, 1, 4 divided by 2, 2, and 0 divided by 2, 0. Then R3 minus R2 gives us a row made of only zeros. Recall that when solving a system of linear equations and we obtain such results, this means we have an infinite number of solutions. And this is because the number of pivot columns is less than the number of columns, and we also have no absurdity or contradictory statement, since 0 is actually equals 0. And with this, we are going to see how to find the null space of A. So we will write our equation as a system of linear equations, and we have 1 x1 plus 2x2 plus 2x3 plus 2x4 equals 0, which is extracted from this row. Then for the next row, we have 0x1 plus 0x2 plus 1x3, which is this, plus 2x4, which is equals 0. From this, we have x1, which is equals negative 2x2, from sending this term to the right side, minus 2x3, this to the right side, minus 2x4. x2 equals x2. The reason we are saying or repeating the fact that x2 equals x2 is simply because there is no other equation which contains x2. So we just simply have to say x2 equals x2. Then, since we have x3 plus x4 equals 0, we can send x4 to the right side, and then we have x3 equals negative x4. No other equation is left as we've exhausted the first two equations, so we just say x4 equals x4. We rearrange x1. We have minus 2x2, which is this, minus 2 into x3 plus x4. But x3 plus x4 equals 0, so this part becomes 0. And this gives us x1 equals negative 2x2, x2 equals x2, x3 equals negative x4, and x4 equals x4. This implies that the null space of A is not just made of one vector, which would have been the case if we had a unique solution, but made up of a set of vectors which verify this condition. X must be such that x1 should be equals to negative 2x2, x2 should be equals x2, x3 equals negative x4, and x4 equals x4. So what we need to do here is we actually select x2 and x4, and then we generate x1 and x3. To write this better, we have the null space of A is made of the linear combination of the vectors -2, 1, 0, 0, 0, 0, -1, 1. We can note them as v1 and v2, where x2 and x4 are constants. To obtain the vectors v1 and v2, what we do is we take out the constants which we need to be able to get the other constants. In this case, x2 and x4 are needed to generate x1 and x3, and also even x2 and x4. So we have x2 and then x4. Now, the vector we're going to attach to x2 is this vector, -2, 1. And that's because on the first we have a -2 attached to x2, and here 1 to x2. For the next two, we have no x2, so we can suppose that a 0 is attached to x2 here and a 0 attached to x2 here. And that's why we have -2, 1, 0, 0. For the other vector, we're looking for what's attached to x4. On this first, we have no x4, so we consider it to be 0. For the next, we have no x4, so we consider it to be 0. For this, we have -1 x4, so we have -1 and this 1. With this, we see clearly that the null space of A is actually the span of the two vectors v1 and v2. So, the null space of A is the set of vectors which are formed from the linear combination of the vectors v1 and v2. Let's take an exercise. Suppose the matrix H. Is this vector an element of the null space of H? Is this other vector an element of the null space of H? Then find the null space of H. To check if a vector is an element of the null space of a matrix, all you need to do is multiply the matrix by the vector. And if you have the 0 vector of Rm, then that vector is part of the null space of the matrix. For the first case, we have a vector with 4 elements. In matrix notation, the vector is noted as a 4x1 matrix. Multiplying a 3x3 matrix with a 4x1 matrix is invalid. So the first is not part of the null space of A. For the second, we have a 3x3 matrix and a 3x1 matrix. But after multiplying the two matrices, you don't obtain a matrix which is 3x1 and whose elements are all zeros. So it is not part of the null space of A. For the third question, after solving the system of linear equations, you should obtain x1 equals 0, x2 equals 0, and x3 equals 0. So this means normally this is actually the null space of A. But recall that when defining the null space of A, we said the 0 vector of Rn should be excluded. So this is not the null space of A. And in this case, the null space of A is an empty set. So the null space of A for A being that matrix doesn't exist. And this is always true for matrices which have n pivot columns.